Okay, in this fluid dynamics problem, which is to say a problem involving moving fluids, we're going to use Bernoulli's equation, continuity of flow, which is conservation of the actual mass of the water that's flowing, and projectile motion to solve for the nozzle size of a hose that's squirting water. Okay, so we're given some information here about a person that's holding a garden hose. We're told that the radius of the hose is 2.5 centimeters, and we were given the flow rate of the water coming out of the hose in volume per second, so cubic meters per second, and it's 9.48 times 10 to the negative 4. And it is spraying water horizontally as shown, right? So the initial velocity is entirely horizontal, and the person is holding this hose 1.35 meters above the ground. What is the initial velocity of the water as it leaves the hose and the range the water sprays before hitting the ground? Okay? So how do we solve for this problem? Well, we just need to relate the flow velocity to the initial velocity. Okay? So let's think about what is going on with that. So we want to use kinematics to find the horizontal range x, which means we will need v naught. We'll actually need to find that numerically, and the time that the water spends in the air, which we'll do using kinematics. Okay, but first, something we haven't seen before is how do we relate that initial velocity to flow rate? Well, flow rate is volume per time, but we want meters per time. So what we want here is flow rate divided by area, because that will give us velocity. Okay, and you can see it makes sense in terms of units, because we obviously have the meters per, or cubic meters per second here, and then here we just have square meters, which will leave us meters per second, the units of velocity. And it also makes sense conceptually. Okay, so our flow rate, 9.48 times 10 to the negative 4 cubic meters per second, and that's going to be divided by our cross-sectional area, which is pi r squared, so pi times 0.025 meters squared. Okay? So seeing what that gives us numerically. All right, gives us 0.483 meters per second, our initial velocity in the x direction. All right, so now onward to kinematics. So here I've shown that if we just consider the motion in the vertical direction, and we look at our final height of 0, our initial height as h, we have no initial vertical component of velocity. Here's our acceleration in the vertical direction, which is just gravity. So that gives us the result that the time in flight is just the square root of 2h divided by g, right? And the g is inside the square root, a little more obvious. So here I've just plugged in the values, and that gives us that the water spends, any given molecule of the water spends about half a second in the air. So then that will easily give us the range, which we were asked for. So spraying water horizontally. Let's see. This is the height above the ground. Oh yeah, what is the initial velocity? So that it leaves the hose, which we solved and put a box around it. And then, oh yes, the range the water sprays before hitting the ground. Okay, so let's go ahead and plug in for x. So say, okay, so x is then just going to be v naught x, which is of course non-zero, unlike v naught y, which was 0, right? Times that time that we solve for, the time in the air. It's often called the time of flight. Okay, so we'll use the velocity we found, 483 meters per second, times our value of 0.525 seconds to get our number here. So let's plug this one in the calculator so we don't have any rounding, because I didn't show the calculation for the initial velocity, so I'm going to do that now. So we can copy that value without rounding. So 2.48 times 10 to the negative 4. All right. And that's in the numerator. In the denominator, we have pi r squared. All right. So 0.025 for, yes, our 2.5 radius, good. And then that's going to be squared All right. So it didn't like something. What did I do? Oh, wrong type of negative sign. There we go. So 0.501. Because I inverted my numbers here, so it's supposed to be 48, not 84. So 48. There we go. Okay. And now let's open up a square root to actually find our time in the air. So 2 times 1.35 divided by 9.8. Okay, there's that time, and then let's multiply them both together to get our range. So just this multiplied by the initial velocity, time multiplied by initial velocity. So we get a range of about 25 centimeters. Okay. So let's go ahead and put that in. So 0.253 meters. Okay, so onward to part B of this problem. And I just resized to make room for part B. So in part B, we're asked if the person wants to spray 2 meters, right, so to multiply their distance by about 8 times, what percentage of the nozzle area will they have to cover up? Okay, this is an interesting question, and we can kind of see how we combine our information, but let's think how we'd set this up symbolically. All right, so the first thing that I show here is that if we want our range to be 2 meters, then we need a new initial velocity, which I'll call v naught x. And so then what we'll do is then solve for that required initial velocity. And when we do so, right, so x over t, plug in our 2 meters, and then when we, of course, multiplying by the time, or dividing by the time in flight, we get a required velocity of 3.81, right? So it has to be coming out significantly faster, which makes sense, right? Rather than half a meter per second, it has to be nearly 4 meters per second. Okay? So, and it actually makes perfect sense because it's a linear relationship between time, or rather horizontal distance, and initial velocity, right? Because we see it here, linear relationship. Okay. So with that information, then we should be able to put that back into our flow rate, so this equation right here, and actually solve for the area of the hose. So basically we'll find the necessary area and then think about what happened. Okay, and actually maybe a better way to think about this is to go back to continuity. So let's consider the continuity equation. So I'll point that out here. So I'll say, and continuity gives us A1 V1 equals A2 V2. All right. I'm gonna actually write that in terms of the notation of this problem. So I'll call it A V and equals A naught, or actually A naught V naught equals A naught prime V naught prime, because we already used the V naught prime as the new initial velocity, so then we need the new cross-sectional area of the hose, and this was what it was originally. Okay. Okay, so here I've shown that if we want to find this new, smaller cross-sectional area, A naught prime, that gives us our larger initial x velocity of the water, we'll use continuity, so this equation here, and right, so here was the original cross-sectional area, which pi r squared, where r was 2.5 centimeters, ends up giving us a cross-sectional area of 1.96 times 10 to the negative 3 square meters. There was the velocity that was resulted in that cross-sectional area with our fixed flow rate, which hasn't changed, right? So there's been no change in the flow rate in either parts A or B of this problem. And now here we're dividing by our new faster velocity, which means that we have to have a new smaller cross-sectional area, right? So it's almost 10 times smaller, right? It's 1/10 the original size, because instead of 1.96 times 10 to the negative 3, it's 2.49 times 10 to the negative 4 square meters. Okay, so now with that information, we can say, well, then what's, the question asked for the percent. I mean, it could have just asked for the new area, what's the required area, but it was kind of interesting to think about, well, how much do you have to actually cover, in this case with your thumb, or the person has to cover with their thumb, in order for the water to go faster and get that greater range. Well, let's see. Well, they had to cover, about 90% if we just look at it, but let's actually set that up and find the percent difference. Okay, so putting in the percent difference as just the original cross-sectional area, A naught, minus the new smaller cross-sectional area divided by the original, we have that 87% of the hose nozzle had to be covered in order to get the water to go about 8 times further. Right? So quite an interesting result, right? And you know, maybe it was intuitive up to the point of saying, oh, well, we have to get the velocity to be 8 times bigger to get 8 times their horizontal range. But then to relate that to how much of the nozzle has to be covered, we can't really do that in our head because it's not a direct relationship like that. Multiply by 8, multiply by 8. Instead, we get up with 87%, but quite an interesting result. Okay, thank you.